let's look at G-C.B.5, worksheet number 2. This deals with radians and its connection to arc length. Now there's actually a really cool connection to arc length with radians, and that's why actually it's introduced at this stage. Let me give you an idea here. First of all, what is a radian? Well, it is an angle where the radius is the arc length. Now, let's just give you an idea. Let's tell you the radius is 10 centimeters and our angle is 2 radians. Now, if I asked you how big is the arc length of a sector that has an angle of 2 radians and a radius of 10, it's a very simple answer, because 2 radians means 2 radii along the circle, right? This angle here being 2 radians would mean that the distance here is 10 and 10 make 20. So really, we find a neat little formula when we're in radians. The arc length is equal to the angle in radians times the radius. So this little formula here becomes a very powerful one when we're in radian measurement, because when I tell you how many radians you have, I'm really telling you how many radii we have along the edge of the circle. And so if you know the radius, it's the angle times the radius. It's that simple. Now, I will say that, not all radii are like this, but let's say they say that the angle is pi over 3. Now, if you don't know this off by heart yet, pi over 3 is like 180 divided by 3. This is like a 60-degree angle. And if the radius was, I don't know, 3 centimeters, the arc length would just simply be pi over 3 times 3, and the arc length would be pi centimeters long. So if your radius is a 3 and you're at that 60-degree angle, or pi over 3, so what we're talking about, pi over 3, I don't know, looks about like this. If our radius is a 3 along there, right? So if that's a 3, then it would be how much our radius is times the size of our angle gives us that walk along that edge. And in this particular case, turns out to be exact length of pi. Now that might feel awkward for a few of you, but it's not that bad. So the main idea is that this little formula, and it works in this worksheet, they'll give you the arc length, they'll have you work backwards to find r and vice versa. They'll give you angles in degrees. They'll tell you that it's 60 degrees and you'll say, oh, that's pi over 3 in radians. So you might have to do a little converting to get around. Let me give you an idea why this is such a nice little concise formula. Normally, if you're asked about the arc length, you're thinking about 2 pi r, because that's the arc length of one full circle. Now, if you don't go the whole way around, you go a percentage of the way. So you go a certain percentage of the way. Now, if the total circle walk is 2 pi, that's the full walk, full angle. And the amount of the angle we don't know. Is it halfway? Is it a quarter? Is it 3/8? Whatever it is. But basically, this would represent a percentage of the entire arc length. Now, watch what happens, which is kind of fun. The 2's cancel, the pi's cancel, or divide out, better term. And guess what we get? We get the angle times r. There it is again. Very nice little relationship. So when we are in radian measure, the arc length is just simply the angle in radians times the radius. It's not that bad, I promise. And what they'll do for you, they might say to you, hey, the arc length is 3 pi. What's the angle if the radius is a 6? Now you say, well, how do I figure this out? Well, I would divide both sides by 6, I get pi over 2 equals theta, and I find out that theta is pi over 2 radians, or if you don't know by now, 180 divided by 2 is 90 degrees. That would be a 90 degree angle if that was its arc length and that was its radius. All right, good luck with that.